So this is the second video on neutral geometry, and in the first video we looked at all of the axioms in the SMSG. Sorry, that's up here. In the neutral geometry section overview, we looked at the SMSG axioms 1 through 15. So neutral geometry is all of the theorems we can prove without actually making an assumption about parallel lines. And just to let you know, the big broad brushstrokes is that we can rule out spherical geometry. Spherical geometry can't happen with Euclid's first four postulates, but hyperbolic geometry can. And that was the problem that they were having. That's why Euclid's fifth postulate was in debate for over 2,000 years. We had to sort through those nuances. So hopefully you'll understand more about this after we do neutral geometry, this section. So section 2.1, we have a job that's somewhat more difficult. We have a bunch of definitions to get through. Why? The SMSG axioms are this huge ski jump that sent us flying past all kinds of content. But they express such detailed and robust mathematical concepts, we have to spend some time sort of backfilling all the things that they defined for us in just the first 15, or excuse me, they used concepts that weren't defined. So we are using our standard undefined terms, right? Our undefined terms are points, lines, and either on or intersect, right? However you'd like to think of it. And so these are the definitions that we need. We're going to start with a segment, and the segment, and you see different segment definitions, and you need the word between to understand a lot of segment definitions. They say, oh, it's the points A and B and all points between them that lie on some line. Well, that's what we'd like to say. The difficulty is we can't because we haven't defined between. This is a circularity that you'll find in a lot of K-12 geometry textbooks. So here's a segment definition that doesn't use the idea of between. We're going to use that idea in just a minute. So we're going to have the endpoints, right? A segment. And by the way, remember we get all of our set theory stuff. So we're calling it a set of points. So we know that the elements inside the set are points. And the whole set is going to be the segment. So you get the endpoints A and B and all points P such that P is on the line AB. Okay. And then here's what we're doing to get the between part, right? We're doing the distance from A to P plus the distance from P to B equals AB. So let's think about that, right? If I have a point A and a point B, right? This distance is going to be longer. P can't be up here, right? Because this distance would not be equal to the distance between A and B. So we're looking at points that are on the line. They have to be on the line. Why? Well, because this distance would not work out otherwise. Okay, so our definition relies on the distance postulate and the fact that P has to be on the line if there's going to be an equality here. So now we're going to define between, and it's important to notice, right, that it has to be on a line or segment that joins these. So when I say that a point B is between A and C, I'm saying that it's on this line segment AC, but it's not equal to either of the endpoints, right? That's what we mean by between. It's in the interior of that segment. And the segment comes along for free whenever I say the word between. Now, these are concepts that aren't quite as difficult to prove, or excuse me, to define. Segment congruence. Notice, however, that we're saying that we're using the distance postulate here, right? These real number distances are equal, right? If the distance between their endpoints are equal, then the segments are congruent. A circle is a set of all points that are equidistant from a point called the center. That's very standard. Angle congruence, now we again have these real numbers because we have angle measure. Two polygons are congruent, so now we are using a combination of segment congruence and angle congruence for the polygon congruence, right? So if there exists a one-to-one correspondence between their vertices such that all corresponding line segments and corresponding angles are congruent, right? So I have to apply the line segment congruence to all the line segments and the angle congruence to all of the angles. Now, this is a proof I've already done, and I'll put this on D2L for you guys, but congruence is an equivalency relation, and all the different congruences, the line segment congruence, the polygon congruence, angle congruence, everything that can be congruent in geometry is actually a congruence relation. And this is why in a lot of geometry proofs, you'll see people put in the word, right, the reflexive property. Or they'll just use the word reflexive. What are they saying? Well, they're saying that we have an equivalence relation. That's one of the properties of algebra that come along that we're allowed to use. And then transitivity we use all the time, right? That if A is equal to B and B is equal to C, then A is equal to C. That's a theorem, and that gets proven right away. That's the first theorem that we have. Collinear, oh, and by the way, to prove it is not hard. They're all based on the distance postulate for segment congruence or the angle measurement postulate for angle congruence. All right, so collinear just means we have 2 points on the same line. Intersecting line just means that 2 points intersect. Concurrent lines, 3 or more lines intersect on the same point. And then it's important to note that parallel lines do not intersect. So sometimes in K-12 schools, you'll have this definition where they say, oh, these parallel lines, they're equidistant everywhere, and they measure the distance between them, and they try to get this idea that equidistant everywhere is what we mean by parallel lines. Well, that's true in Euclidean geometry, but it's not true in hyperbolic geometry, where you have parallel lines that look like this. And the idea here, and again, it's a nuance, but we're going to discover why hyperbolic geometry and Euclidean geometry are so closely related. But these lines are not everywhere equidistant, and they still do not intersect. And this is what allows for, infinitely many lines to be going through the same point and be parallel to this line L. Again, do not intersect is our definition of parallel. Now, when we go to define array, we're going to use this between idea, and you can see the animation, hopefully. And so array is just a half line. That's what they use, right? It's a line, but I have a point, right? So I have a point A, and then the line that goes out from A in one direction or the other. And so we're using the idea that A cannot be between C and B, okay? So if you see the animation down here, only when C is down here in our perspective to the left of A, that's the only time that A is between B and C. So when C is above B, you have B is between A and C, and now you'll see C go below B, but we still have C is between A and B. A isn't between B and C when the C stays up to the right. So that's the definition of array. And angle, some of these are very straightforward with SMSG. The union of two rays which have the same endpoint, straight angle, an angle whose rays are distinct but collinear. Okay, so remember the definition of an angle means that I have the union of two rays with the same endpoint. So how can I have the same endpoint for the rays and have them be distinct? That means they have to be different. I can't draw this same one again. But collinear, well, then it has to point in the opposite direction. And sorry, that's not a very nice straight line there for this particular ray. But that's what we mean. A straight angle is an angle, right, which forces the similar endpoint. And I have to have two different rays, but they have to be on the same line. So that constrains everything for us. Now, the angle interior is another situation where I'm using the idea of betweenness. So let's see if we can get this figured out, right? So the angle interior, the way we're going to define it is we're going to put a point X on one of the rays of the angle, and we're going to put the point Y on the other ray of the angle. And we're going to say that if a point P is between X and Y, then it's in the angle interior. Okay, so let's start up the animation and you can see that. So the line segment XY, X is on one of the rays, Y is on the other, and then P can kind of be anywhere in between that we like. All right, so that's the definition. Let me pause that. So if you ever when I embed these animations, you can play around with them. You can zoom in and zoom out with your mouse scroll button, and certain points can be dragged around so you can see different things if you want. So convex polygons. Now this is interesting. People talk about, the mouth of the cave, it's concave, but when you understand the actual definition of concavity and convexity, it really just has to do with whether or not, when I draw a line segment connecting 2 points in the figure, whether that line has to be wholly inside the figure, like it is for convex, or whether it can jump outside. So let's start this animation and you'll see. So on the left where it's convex, it doesn't matter where I put the X and the Y. No matter where I put the X and the Y, and no matter how I drag this around, the X's and the Y's, as long as they're in the interior of the polygon, the entire line segment that connects them is also going to be in the interior of the polygon. Now, what happens with concave? Well, with concave, there are lots of places where I can pick, an X over here and a Y over here that's in both of the points are in the figure, but when I connect them with a line segment, part of that line segment jumps outside the figure. Okay, so a convex polygon is one where no matter which 2 points I choose, the entire line segment joining them will be inside the figure. And concave says, well, there exists 2 points, right? So I can choose two. I might have to narrow it down to just a few possibilities, but there will be some place where I can choose 2 points and where the line segment that connects those 2 points has to travel outside the polygon. If it travels outside the polygon, it's concave. So the midpoint, very straightforward. We're using the distance postulate here to say the distance from C to both endpoints is the same. And remember that this notation means distance, right? And this notation means segment, right? So if I say AB, right, I'm talking about the distance from A to B. And if I put the segment bar over it, I'm saying that I'm referring to the line segment AB. So let me kind of explain where that might come in. AB is not equal to segment AB, right? When I'm using segment, I need to use congruence, right? These line segments are congruent. But if I'm talking about the distance from A to B, that is in fact equal to the distance from A to B. So it's important to realize that when you're using this notation here, you're actually saying there's a real number. There's a real number that specifies the distance between the two of them. Here, you're referring to the whole line segment as a geometric object. Angle bisector, notice we're going to use we're using the idea of between, but in the same way that we used it for the segment, we're saying, hey, if the measure of the angles are equal, right? And by the way, I'll switch this notation in the book to measured angle. I'll get to that in just a minute. The right angle is an angle with measure 90 degrees, and acute has less than 90 degrees, and obtuse has greater than 90 degrees. Those are very standard. And the perpendicular bisector is exactly what you think. If I have a line segment AB, right, then the perpendicular bisector, it goes through the midpoint of the 2 points and is at right angles. Notice that we don't have reflex angles defined yet. We're only allowed to have angles between 0 and 180 degrees, and I did mention that when I was talking about neutral geometry axioms. That's all we get from the axioms. We don't get reflex angles, we have to define them. Vertical angles, anytime that two lines cross, right? We have vertical angles, the angles across from each other. There's also another pair of vertical angles when those two lines cross. Now, linear pair. So I wouldn't normally define this. This isn't a standard geometry concept, but your SMSG axioms use it. Okay, so we have to define it. If they're going to use it, we have to define it. So what is a linear pair? It's two distinct angles that share a ray, and their non-shared rays are collinear. Their non-shared rays are collinear. Okay, so we have an angle here and another angle here, right? So they share this ray. This ray here is the shared ray. Okay, and the non-shared rays are collinear. So two distinct angles that share a ray and whose non-shared rays, right, are collinear. Hopefully that makes sense. And the reason we need it is because SMSG axioms use linear pair to define supplementary. And here we go. Here's our definition of supplementary, which actually isn't a definition. It comes straight from the axioms. It's the supplementary angle postulate, and it says if two angles form a linear pair, they are supplementary. Okay, and again, so since this is an axiom, I probably wouldn't have to define linear pair, but it's just easier to go ahead and do it because there is a way to define it. And I didn't need to do this, but I'm like, well, if you're going to use the right angle pair to define, you're going to use the linear pair to define supplementary, right? So linear pair to define supplementary, why not just go ahead and define what a right angle pair is and use that to define complementary? And we'll just use the same setup for both. And so a right angle pair is two distinct angles that share a ray whose non-shared rays form a right angle. So now you have some angle like this, and you have an angle that shares this ray with it that looks like this, and there's a right angle. So now this shared ray is in the middle, and the non-shared rays form a right angle, so that's a right angle pair. And now we have a nice way to define complementary in exactly the same way as we did with the supplementary angle postulate. We'll say complementary angles form a right angle pair. Okay, so the final thing in the unit is the theorems. So I mentioned this already. I'm going to prove that all congruences are equivalence relations and therefore reflexive, symmetric, transitive. You guys are going to prove this. Somebody gets to prove that every line segment has exactly one midpoint. Now I want to point back to the Young's geometry, finite geometry stuff we did. And so this is actually two proofs. It's existence and uniqueness, right? So you have to prove that there is one, that there is a midpoint, and you have to then assume that there are two midpoints and prove they're the same, right? So do both an existence and a uniqueness proof. Every angle has exactly one bisector, same exact thing, existence and uniqueness. However, the thing you use for theorem 3 is the angle measurement postulate, and for part 2 you use the distance postulate. So basically they work the same exact way, but remember to do an existence and uniqueness proof. Supplements and complements of the same angles are congruent. Well, this is going to look a lot like vertical lines because here I have, let's see, so let's focus on this angle here, which I'll double mark, right? This single marked angle over to the right is supplementary to it, and then I'll triple mark an angle over here. So the triple marked angle is congruent to the double marked angle, and the single marked angle is congruent to the double mark, is supplementary to the double marked angle. Since they're both supplementary to the double marked angle, they're both congruent to each other. And you'll notice that once you have theorem 4, then theorem 6 is hopefully going to be straightforward. And we'll use that. So supplements and complements. So there's 2 proofs here, right? So you have to do a complete proof for supplements and then another complete proofs for complements. Then theorem 5, the intersection of 2 convex polygons is convex, and that's mine. I'm going to prove that. It's not that difficult, but it's not a typical geometry proof that I want you to do. I want to focus more on the standard geometry proofs. Then the final thing I want to mention are these last 2 axioms, Paschas axiom and the crossbar theorem. So we're not going to prove these because we have the plane separation postulate. The plane separation postulate gives us what we need, along with the ruler postulate that forces every line to be continuous and complete. But this is what geometers realized in the 17th and 18th century, that they weren't guaranteed to have all the points that they needed, right? So Pasch was saying that, hey, let a line come through this triangle, and it has to intersect somewhere in the interior of that line segment AB. And they said that if it intersects one side of the triangle, then it must intersect the other side of the triangle. Now, this looks like it could intersect at C, and I'm sorry about that, but to have the animation work, this line actually disappears for a split second right at C. At least that's what I tried to do, but you can't see it, right? It happens so quickly. But anyway, the moral of the story is it shouldn't appear when it's through C, because that's contradicting this no vertex of a triangle. But the idea is if it goes through side AB, then it also would have to travel through either side AC or side BC. And so proving this is important. Why? Well, how do we know that if I start at B, that I go across here to some point that's exactly the square root of 2 units away from B? And how do I know that there's a point there, right? How do I know that even though it looks like, you know, this line goes through a point, that the point is actually there? Well, that's the point of proving Paschas axiom, but this also kind of explains the type of detail that we don't have to worry about too much. And the crossbar theorem is the same. You can check that out, but it's pretty much the same idea as Paschas axiom. It's forcing the intersections of lines to behave like we want them to, like we need them to. And we can prove from first principles that this is true, that every line in the geometry behaves like the real number line. But these were the steps classically that we had to go through, right? This is the kind of stuff we had to do with these primitive axiomatic systems that were independent, right? And this is what the SMSG does for us. It skips past some of these they're not tedious particularly, but they're not the kind of geometry that you want to spend time doing, especially not in high school geometry. You don't want to fiddle around with this. And again, the plane separation axiom, that's why it's there, so that we get lines that cross, that intersect. We get that intersection point, and we know that those lines are complete and continuous. So I'll be back with 2 more units on neutral geometry, but this should give you a nice overview to start looking at the proofs in this section that you need to do.